All right, welcome back. So here's our next example. So this is still from 7.1, or example 6. So let me zoom in a bit. What are the directions? It says substitute x equal to tangent theta into the expression square root of 1 plus x squared and simplify completely. We're assuming that theta is between 0 and pi over 2. Let's think about why those values are important. So 0 to pi over 2 means that our thetas are in this first quadrant, excluding 0 and excluding pi over 2. That's why I put open circles. So theta in this range, if we think about tangent, tangent is sine over cosine. Cosine is going to be in this range down here. So cosine is positive, and sine is in this range up here. Sine is positive. Okay, which tells us that tangent is positive. Okay, cool. But now for the fun part. We are asked to substitute. Okay, so here we say x is tangent theta, and we're going to substitute into square root of 1 plus x squared. So this is a very important technique. You're going to do this a lot in calculus. So first we're going to start with the original expression, the square root of 1 plus x squared. Now we substitute, which means we're going to replace x with tangent theta. Okay, so we have square root of 1 plus, in parentheses, tangent theta squared. You can just simplify this and write this as 1 plus tangent squared theta. And now you should be thinking, okay, remember 7.1 is all about the trig identities. And hopefully you remember that this is actually one of our Pythagorean identities. And which one is it? The Pythagorean identity is that 1 plus tangent squared theta is equal to, think, secant squared theta. Okay, so now that I know that I can replace that with secant squared theta, I have a square root of that. Okay, a square root of a square simplifies to absolute value of secant theta. And then you're thinking, wait, why am I using absolute values? Well, because every time you do even, if n is an even number, then you have to do absolute value of x. And actually, I should just write it like this. Okay, because remember, if you undo, so let's think through this simple example, right? If I have square root of negative 2 squared, if I square the negative 2, I get 4. And if I do the square root of 4, I'll get 2. So I don't get back the original value. I get back the absolute value. Okay. So how does that help us with this problem? Well, it leads us back to this little the unit circle that I drew. In the unit circle, the reason I was doing that, it was to really highlight, well, if theta is in this range of values, then cosine is positive and sine is positive. I'm looking at secant of theta. So because of this extra assumption, actually I can simplify this and say, well, secant is going to be positive, so I can get rid of the absolute values, and there's nothing more to simplify. I think I can just put a box. That's my answer. So pretty good, straightforward problem, I think. Really just, made it too tiny. Substituting, and then of course at some point, if it's a good problem, you're going to use some of the identities to help you simplify it. And you could write this as 1 over cosine if you prefer, but I think leaving it as secant theta is perfectly acceptable. The really key step after using the Pythagorean identity was taking the square root of a square and thinking through whether we need a positive sign, a negative sign, or if we need to keep the absolute value. All right, thanks for watching. That was example 6 from 7.1. See you in the next video.